Dear ladies and gentlemen, respected colleagues and participants in the International Conference on Built Environment Science Technology. Initially, I would like to thank you cordially for your attention as well as for giving me this unique opportunity to present this research paper by the utilization of a recent well-known design platforms and applications. Furthermore, I would like to make a brief introduction of myself. At the present stage, I am appointed as an assistant professor at the Laboratory of Building Construction and Building Physics, which belongs to the Department of Civil Engineering of the Aristotle University of Thessaloniki in Greece. In that respect, my main research interests concern building technology with a special emphasis on the dynamic thermal response of building configurations as well as the thermal behavior and the energy performance of building structures. Lately, I am also studying the fire responsiveness of building assemblies under certain environmental conditions and constraints. Within this framework, the present investigation aims to analyze the thermal defensiveness of hollow clay brick masonry walls subjected to the fire action or else, as we may say, exposed to elevated temperatures. So, the main objective of this study is to analyze the thermal performance of a masonry wall under a fire action that corresponds to the eminent standard temperature time curve of fire as specified in the European standard, the Eurocode 1. In that respect, temperature variations on the non-exposed surface of assumed masonry walls revealing their thermal responsivity and self-defensiveness can be determined by adapting a 3D model and an eminent dynamic thermal simulation program. Therefore, this work shows the significance of the thermophysical properties of a clay material and the importance of the thermal emissivity as regards heat transfer processes for examined assemblies. Apart from this, a few slides regarding the thermal behavior of insulated wall configurations are exposed to highlight the influential role of the insulation layer on the heat flux and the corresponding temperature variation in the time domain. Firstly, it is essential to point out that fire protection shows an immense interest in a global scale. Severe consequences of fire incidents and accidents address the demand to enhance the design of building shells. In order to mitigate this impact, passive as well as active measures demonstrate an efficient way to fulfill this critical demand. Regarding passive approaches, it is worth mentioning that the resistance and the reaction of building materials, building elements and building structures underline some of the key issues of this problem. To address these points, mostly national fire regulations specify prescriptive necessities based on the shown experience. Passive fire protection concerns fire and smoke prevention measures such as the design of the building and the compilation of structure elements on the basis of building materials arrangement. On the other hand, active fire protection focuses on fire and smoke control measures. These are fire and smoke detection systems, fire suppression systems, portable automatic fire extinguishers, and at last, smoke extraction systems that are regulated by naturally or forced control ventilation schemes. With respect to fire extraction systems, it is essential to point out that they can ameliorate sharply the performance-based design of buildings and facilitate the evacuation process. Since the core attention of this investigation refers to passive fire protection of buildings, it is important to state that the installation of building components is critical. Accordingly, the position of building layers, in addition to the geometrical characteristics and the thermophysical properties of building materials, can modify and shift substantially heat fluxes and temperature fluctuations. This implies also the exposed temperature peaks that is a central issue of this presentation. In the literature, someone can notice that the thermal response of masonry walls strongly relies on the assembly of involved materials. Moreover, in many studies, the thermal properties of a clay material are shown to be influential in terms of heat flow through the masonry. In other papers, the importance of air cavities within clay hollow bricks is clarified with respect to the thermal emissivity of involved surfaces. So, as seen, a special consideration is given on thermal processes through masonry walls. This persistent dedication makes obvious the stress of this study in order to further clarify the gray zones that still remain. Moving forward, masonry walls and building materials are illustrated in the following slides. As can be seen here, the analyzed building assemblies correspond to an insulated masonry walls. A masonry wall consists of conventional hollow clay bricks which are laid in and bound together with cement mortar. In that respect, the thickness of each clay brick unit of a masonry wall is 25 cm, while the thickness of the bond between bricks and mortar is considered to be 1 cm. In addition, both sides of a brick wall are covered with 1.5 cm thick lime mortar. The thermophysical properties of the clay material of brick units, of the brick bonding, and for both coatings are listed in the current table. Furthermore, with reference to hollow blocks, two different types of clay material are examined, referring to lightweight and heavyweight categories. Then again, three sets of thermal emissivity values of the clay material on hollow brick cavity surfaces are considered for the aims of this examination. These values cover from one side to another the entire possible range of emissivity variations in the production stage of building materials. Consequently, the analyzed masonry wall scenarios are briefly stated in this table. As seen, 6 illustrative cases are analyzed. Based on these choices, as it is clear, our main goal is to extract findings that can clarify the general trends shown in analogous cases. As we move forward, the environmental conditions on both sides of the masonry wall should be cautiously selected and specified in order to conduct the transient thermal analysis. With respect to temperature variations on the non-exposed to the fire boundary, a logarithmic forcing function appears to be valid. Thus, this type of variations demonstrate the actual elevation of temperatures due to a fire action incident. Gas temperatures in the vicinity of a fire-exposed masonry wall can be replicated by adapting nominal temperature time curves according to Eurocode 1. As follows, this trend is elucidated by the standard temperature time curve of fire. Temperature variations are aligned with the following equation. On the other hand, temperature values on the unexposed surface of a masonry wall against the fire action show a fixed trend. This trend is expressed by a constant air temperature value for the entire 6 hours period of a conducted transient thermal analysis. So, at this stage, our main concern is to briefly illuminate the key aspects of the transient thermal analysis. This part answers to the simulation program as well as to the model development for the fundamental objectives of this work. To accomplish this goal, a finite element methodology reflecting the main philosophy of the algorithm was taken into account. In this context, a three-dimensional modeling is considered as an adequate technique. In other words, actual transverse heat flows are assessed due to their vital impact on the findings of this numerical work. However, to resolve heat transfer processes for building members, it is necessary to specify the geometry of its structure, the thermal and spectral properties of entailed building materials, and of course, the forcing functions on both boundaries. Within this framework, the following equations demonstrate the theoretical background of this analysis. In overall, these equations make provision for conduction through solid wall sections of assembly, free convection within air cavities developed by the brick hollows, and long wave radiation on the cavity surface of brick elements, and finally, convection and radiation on both boundaries while assuming some basic simplifications that do not disturb the reliability and accuracy of the heat flow evolution. As we proceed to the core sections of this study, simulation software findings showing the impact of the previously mentioned parameters on the temperature's evolution of masonry walls subjected to fire are given in the following parts of this presentation. As it is already mentioned, special focus is being given on the indicated temperatures on the unexposed surface of the clay hollow brick masonry walls. In general terms, the extracted results of this effort in the time domain unveil a gradual increase of the developed temperatures. This is a rational outcome since the fire action presents an elevated logarithmic trend. Therefore, based on this forcing function, someone could say the only way for the shown temperatures is upwards. As shown in this graph, an increase of the thermal emissivity leads to a parallel increase of the resultant temperature of the non-exposed surface. Thus, for lightweight masonry walls subjected to fire, the maximum surface temperatures are as follows. For an emissivity equal to 0.1, the maximum temperature reaches a value equal to 185 degrees. For an emissivity equal to 0.5, the maximum temperature is 220 degrees, while for an emissivity 0.9, the temperature is 235 degrees. It is worth noting that as the value of the thermal emissivity rises, its effect on the temperature values weakens. Moreover, the rate of temperature increase declines as asymptotically approaches a constant value. In addition, from the graphs in this slide, it can be observed that variations on clay material properties affect the thermal response of heavyweight masonry walls in a similar fashion. For this case, the corresponding temperature values of the non-exposed surface are as follows. We have, for an emissivity 0.1, a maximum temperature 180 degrees. For an emissivity 0.5, 240 degrees. And finally, for an emissivity 0.9, a maximum temperature approximately equal to 265 degrees. It becomes apparent that the thermal behavior of a masonry wall sharply relies on the thermal emissivity of the clay material. This implies that the thermal effectiveness of low emissivity coatings is essential with respect to moderated heat fluxes through the geometry of the masonry wall. Therefore, brick units integrated with low E coatings are less prone to the engaged fire exposure. Following the findings presented previously, it becomes evident that the effect of the thermal emissivity in terms of heat wave propagation and temperature elevation is dominant. In this regard, the variation trend of temperatures with emissivity is straightforward. The graphs in this slide illustrate the dynamic process of heat flow for both sets of the clay material while assuming a value of its thermal emissivity equal to 0.1. For the entire period of the analysis, the transient thermal behavior of a heavyweight masonry wall is superior as compared to the lightweight assembly. As it is clear, a lower thermal conductivity value improves the overall thermal response of a wall subjected to fire. Nevertheless, a careful examination of the following findings of this work indicate that the thermophysical properties of a clay material, such as the thermal conductivity and the density, can shift the ranking of the optimal masonry wall configurations subjected to fire at a certain time point. In this regard, the green semi-transparent dot reveals this aspect for an emissivity value equal to 0.5. A similar trend is also shown for an emissivity value equal to 0.9. In that respect, the orange semi-transparent dot corresponds to the critical tipping point of this heat flow evolution. This implies that the thermophysical properties of a clay material of hollow bricks should be emphasized at the very early stages of building design and modeling. However, there are several additional aspects that can tremendously modify heat transfer processes through masonry walls and building layouts. Such principal issues capable to revise radically the previous shown trends are the presence of a thermal insulation layer, the flammability of the insulation subjected to elevated temperatures, and the position and allocation of the insulation with respect to the masonry outline. Based on the aforementioned points, the insulation layer can support or not the self-defensiveness of building components exposed to a fire action. Yet, this is another long story that I may have the pleasure to present in another occasion. As seen to the right side of the slide, a general outline of the examined insulated masonry wall is delineated in addition to the discretization of this component with the utilization of the mentioned simulation tool. Evidently, the procedure appears to be similar to that presented previously, while an additional layer is incorporated to assess the effect of the insulation layer. The thermophysical properties of insulation are temperature dependent in order to take into account the gasification process. Within this framework, the following graph highlights that a different wall insulation layout subjected to a fire curve shows a remarkable effect on the temperature response rate and the heat flow through assemblies of masonry walls. It is essential to point out that the above behavior corresponds to a flammable thermal insulation layer, an EPS, with a thickness of 5 cm. As seen, by placing the insulation on the non-exposed surface of a brick layer, the continuous blue and red lines exhibits a more suitable thermal behavior in contrast with the placement of the insulation on the exposed surface, the dashed blue and red lines. So, the unexposed placement of the thermal insulation layer reduces the rate of temperature rise, but still faces critical challenges as the influence of the thermal emissivity is the key factor of a proper design regarding the influential and severe effect of a fire action. To be more precise, the flammable material is stable until 100 degrees approximately, but after that enters in a glass transition phase and above 110 degrees undergoes a rapid thermal degradation. The inflated EPS beads lose their volume and at 150 degrees regain their initial diameter. At 160 degrees, the EPS appears to be at a viscous liquid state and no longer can be categorized as a solid insulating board. Moreover, in this slide, someone can notice that by increasing the thickness of a thermal insulation layer from 5 to 10 centimeters does not affect notably the trend of the presented temperature variations at the backside of the wall. Consequently, the melting process stage from the insulation layer leads to a minor delay of the shown temperature fluctuations. Nevertheless, the influence of the thickness of the thermal insulation layer will be prominent for a non-flammable material such as a common rock wool layer. To conclude, the selection of materials' thermal properties plays a significant role regarding the temperature evolution through building components. Neglecting these aspects may cause severe consequences and repercussions in terms of fire behavior. The effect of the thermal emissivity is vital and it accounts for the majority of present masonry configurations. High emissivity results in an important heat bridge that accelerates the heat wave progress towards the exposed sides. On the other hand, decreasing the emissivity will introduce a secondary heat resistance within the brick unit. Finally, rising gas temperature values relies on the density of the clay material. So, as it is clear, correct decisions should be a priority for engineers. Moreover, building design should reflect the fire safety requests of occupants, while, and finally, our dedication to fire protection affects decisively the fire safety needs. This aspect depends vigorously on the understanding of the basic principles of nature processes. Thank you very much for your attention. For additional information, I remain at your kind disposal in the following email address.
Dr. Karolos J. Kontoleon for sharing us your research project in understanding the fire performance of masonry walls exposed to elevated temperature.
Epoxy adhesives are widely used in the industry because of their high strength, chemical resistance, and the ability to adhere to different surfaces. But almost all of them have low impact strength and low UV resistance, which makes them weak after long-term use, under stress and limitations. To combat all these issues, we are introducing TITE Pro. TITE Pro is a high-performance two-component multi-use new generation epoxy adhesive system with room temperature curing. It has very high impact strength, excellent shear strength, better UV resistance, better coverage, and so much more. And it is to be used for bonding various similar and dissimilar materials such as metals, ceramics, wood, leather, rubber, marble, glass, and a lot of other materials. TITE Pro is very easy to use. The directions to use are really simple. Step 1. Clean the surface and make sure it is free of dust, unsound material, loose plaster, oil, paint, grease, algae, and corrosion deposits. Step 2. Take equal quantity of part A and part B. Step 3. Mix it for 1 minute with the help of TITE applicator to attain uniform color. Step 4. Apply on the surface. Step 5. Clamp or support the surface for 4 hours. It will attain full strength in 24 hours. And that's all there is to it. You can use it for speakers, marble pasting, automobile repair, and hardwood handicraft. TITE Pro.